Okay, so I hope you can see my screen, all of you. Yes. So briefly, I'll just go through what was explained during week 2 lectures. So we learnt about random experiment, which is any experiment whose result can is not predetermined until and unless the experiment is performed is usually called a random experiment. For example, tossing of a coin or rolling a die, or let's say number of accidents in a day or temperature of a city, all of these cannot be determined until and unless that experiment has already occurred. All right. So so these experiments whose results are not determined previously are called random experiment. And the set of, we all know, the set of all possible results of an outcome of a random experiment is known as sample space. Now it could consist of numeric or non-numeric elements as well. For example, if I say tossing of a coin, then the sample space is either head or tail. So it's a non-numeric set. Or if I consider rolling of a dice, then the sample space would be the outcome or the face that appears when we roll a die. So it can be anywhere between 1, it could be 1, 2, 3, 4, 5, 6. Similarly, number of accidents in a day, this is a countable event, right? There could be 0 accidents on a day, there could be 1 accidents on a day, there could be 3, there could be 4, there could be infinite number of accidents on a day. So this set is the sample space for number of accidents in a day. Similarly, let's say temperature of a city, it could be anywhere. Let's say if I say that the temperature of any city, it should be greater than some, let's say 0 degree Celsius or something, 0 Kelvin, absolute 0, something like that. All right. So this set is an uncountable set of elements. This whereas is a countable set of elements. Now this could be countably finite or countably infinite. Like say this one, number of accidents in a day, there could be any number of accidents in a day, but this is countable. So this is an example of a countably infinite number of elements in a set. But rolling of a die, this is also countable. We could have 1, 2, 3, 4, 5, 6. Okay, so this is a finite countable set. All right. So any outcome which is denoted by this small omega should belong to this sample space. Okay. Next, we also learnt about event. So any subset E of the sample space is called an event. So E should be a subset of our sample space omega. Now any event can either be a simple event or it could be a compound event. For example, examples of simple events are the event that an odd number has appeared on a dice roll, or obtaining a tail, let's say in a coin toss, or these are examples of simple events. But there could be compound events as well, where it would generally be two simple events put together, usually with an and in the question. So let's say the event that head has occurred in one coin and tail has occurred on another coin. For example, let's say we roll 2 die, one has occurred in one of the dice, and an even number has occurred in the second dice. So these are examples of composite events. Alright. Now, also we learnt about the axiomatic definition of probability. But before going into probability, for those who have a little bit of mathematical background, I would like to introduce this concept to you, which is a sigma field. So, a sigma field is a collection of subsets of omega if the following conditions are satisfied. Omega should belong to that set of sigma in that sigma field. If A belongs to F, then A complement should also belong to F. And if we have a countable union, if we have elements of that set and we take a countable union of the elements of that set F, script F, then we say that script F is called a sigma field. Okay. So, sigma field, the most trivial sigma field that we can get is phi, which is actually the null set, and omega, which is the sample space. Okay. So, why is this a sigma field? Because this satisfied these conditions. Omega is present in script F. If A is present, A complement is present. So, if phi is present, let's say phi complement is omega, that is also present in this sigma field. Okay. And A1, A2, A3, if they belong to sigma field F, their countable union also belongs to sigma field F. So, here we have phi union omega, that is also equal to omega, that also belongs to this sigma field F. So, this is the trivial sigma field. Usually, it is defined by sets of these type. So, if we have something written within second bracket, it means that there is only one element in this set. These are intervals. Now, open bracket means the numbers are not included in that set. So, if a comma infinity, if we have something like this, then it means that a less than x less than infinity. This is the set. But if we have something like this, minus infinity a, then this implies minus infinity less than x less than equal to a. If we have third brackets, then these numbers are included. For example, if we have a and b, then we can say a less than equal to x less than equal to b. And mathematically, if we have to define, the definition of probability is that if omega is the sample space and script F is the sigma field defined over omega, then a real valued function, set function on the script F which satisfies these conditions, that probability of A is greater than equal to 0 for all A belonging to script F, probability of sample space is equal to 1, and if A1, A2, A3 are mutually disjoint events, which means any AI intersection AJ is equal to phi, then probability of union of the disjoint union of all those elements will be equal to sum of the probabilities of the individual elements. This is essentially called sigma additivity. Okay, this area, this part. So, if these conditions are satisfied, then we can say that the function p is a probability, and this triplet omega script fp is called a probability space. So, in terms of events, when we consider, then let A, if we say that A is our event, or let's say random event, then from the axioms of probability, what we get is that probability of A should be always greater than equal to 0 and less than equal to 1. Okay. The second thing is probability of omega should always be equal to 1, and if we have disjoint events like A1, A2, AN, then probability of A1 union A2 union AN equal to summation of I equal to 1 to n probability of AI. But given that probability of AI intersection AJ equal to, or given that AI intersection AJ equal to phi for all I not equal to j. Alright. So this, if these three are satisfied, then we say that PA is called the probability of A. Okay, we learnt about this. Also, we learnt about a term which is known as relative frequency. Alright. So, let's say AI is an event, then absolute frequency is the number of times event AI has occurred. Okay, and relative frequency is that the number of times event AI has occurred divided by number of times the experiment is repeated. Okay, so for example, let's say we toss a coin, then the sample space would be head or tail. Right? Now this is the experiment, tossing of a coin. Now if we repeat this n times, then we have n sets of this experiment. Okay, and n outcomes from each of these experiments after it is performed. Alright, so then if I define my event E as tail, obtaining a tail, okay, then the frequency, absolute frequency of E would be, let's say I have repeated this experiment n times, and out of the n experiments, let's say m experiments have yielded head and n minus m experiments have yielded tail. Then absolute frequency of tail is nothing but n minus m, the total number of times a tail has come up. Okay, but then if I have to consider the relative frequency, then the relative frequency is the number of times tail has occurred, that is n minus m, by the total number of times the experiment is repeated, that is n. Okay, and we have also learned that when an experiment is repeated a large number of times, then relative frequency will tend to the probability. Alright, or in other words, if we increase the number of times an experiment is repeated, then the relative frequency can approximate the actual probability of that event occurring. Okay, so this thing we have also learned. And also we have learned about representation of sets using Venn diagrams. Alright, so the entire sample space will be denoted by a rectangle. Okay, and events that belong to omega will be represented usually by circles. Okay, so if I have, let's say, two events, then I can represent it by this diagram. This is event A and this could be event B. Then if I say that A and B are disjoint, if I ask if A and B are disjoint, the answer is yes, because there is no overlap between A or B. Alright, so in terms of two events, let's say this is my sample space. This is event A. This is event B. Then this overlapping part is nothing but A intersection B, which means A and B. Okay. Similarly, if I have this, let's say this is A, this is B, then the entire area this area would be A union B, which is either A or B. Alright, if I want to look at the complement, then let's say this is A, this is omega, then this area outside the circle, this is essentially A complement. We write it either with a with C in superscript, or we can write it like this, A bar. Both of these are representations of complement. Alright, so this area would be A complement. There are other two symbols that we should also learn. Let's say we have A and we have B. So this part A but not in B, this one is represented as A minus B, which is nothing but A intersection B complement. This is B. B complement is outside the entire area outside B. Intersected with A is only this part. Alright. So we all learnt about these things. And also if we have something like this, let's say this is A and this is B, then we can say B is a subset of A. Okay. Also, let us learn about mutually exclusive events. So let us have two events, A and B. Since A intersection B equal to phi, if this happens that there is no overlap between set A and set B, then we called, or event A and event B, then we say that A and B are mutually exclusive. Alright, and what do we mean by mutually exhaustive? If we have mutually exhaustive, then it means that, let's say, this set is A and this set is B. Alright, then A union B equal to omega. This is known as mutually exhaustive events. Alright. Okay, so we learned about these things, and also we learned about the axiomatic definitions of probability, and we also saw that the relative frequency is it goes towards the probability of an event. So let us now first show or give a demonstration of how this probability can be extended with that relative frequency definition. So relative frequency of event A, let's say, will be n of the number of times event has occurred and n divided by total number of times the experiment is repeated, and probability of A equals limit n tends to infinity n of A by n. So we have always seen that if we toss a die, or let's say if we toss a coin, this is my random experiment. Then the sample space is either head or tail. Now if I say probability of getting a head, you'll immediately tell me it's 1 by 2. But can we demonstrate this using R? So we'll see what we can do. So I'll pause my screen here and I'll open an R console. Please confirm if you can see my screen. Is it visible?
Yes, ma'am.
Okay, all right. So let's say I want, okay, so now I want to sample, let's say I want to repeat a coin toss 10 times and see what my outcome is. So I'll use this function sample, and from where I'm going to sample, this is my sample space. Either I should have a head or I should have a tail. So I'll just define this like this: sample space equal to this set. Now I want to sample from my sample space. I'm going to define the size, number of samples or number of times I'm going to repeat the experiment. Let's say I'm repeating it 10 times, and I want to, because these are independent random trials, I'm going to put replace equal to true. Okay, so if I run it, first I'll run this one. So here in the environment I have sample space loaded over here, and now if I use this command, I am going to see the outcomes of, these are 10 outcomes of the 10 trials. Okay, if I repeat it, this is going to change. So let's say this is, so you see, since we have not set any seed, every time we are running this command, the outcomes of the 10 experiments that I'm doing is changing. Alright, now if I want an absolute frequency of each of the outcomes, then what am I going to do? For absolute frequency, I will give a command which is table. Okay, so table of this experiment. So let's say I'll rename this variable into something. So this is my sample drawn. So sample drawn is this thing. Okay, 10 outcomes from 10 repetitions of a coin toss. Okay, now I want a distribution or the absolute frequency of each of the outcomes of my sample drawn. So I'm going to write table sample drawn. So here you see in this console, it is giving me how many times head has appeared and how many times tail has appeared. So in this sample that I have drawn, there are 4 heads and 6 tails. Is it okay? This is the absolute frequency of heads and tails. Now if I want to get the relative frequency, what I am going to do is that I am going to divide it with the total number of times, that is the size of the size parameter here. So relative frequency would be table of sample drawn. I either write 10, or in order to be more general, I should write the number of elements that are there in this array. So that I'll get with this length command. So length of sample drawn would tell me how many times we have repeated the experiment. So see, if I run it, then I am seeing that relative frequency of heads is 0.4 and relative frequency of tails is 0.6. Okay, so now what we want to show is that relative frequency tends to probability when n is large. Okay, so let's see how we can demonstrate this thing. So let us now draw samples of different sample sizes. Okay, all right, let's say initially let our n be 10. So for 10 we have sample drawn, but I'll just repeat this once again. Rename it, let's say sample drawn 10. Okay, let us repeat sample drawn 50. Let us change the sample size now to 50. Okay, so then accordingly we have to change the size parameter. So sample drawn 50 would be sample from sample space, size equal to 50, replace equal to 2. Let's say here we have n equal to 100. So sample drawn 100 equal to, here we'll change the size parameter. Okay, let's say 1000. Sample drawn 1000, 10,000. We'll also see n equal to 10,000. Sample drawn 10,000. Alright, so let us just run these one by one. Sample drawn 10, sample drawn 50, sample drawn 100, 1000, 10,000. Okay, now let us see the relative frequencies. So it would be table of sample drawn 10 by length of sample drawn 10. Okay, similarly, so this will be T10. T, how much is 50, would be T100, this will be T1000, okay, and then we have T10,000. Okay, so T1, T2, 50, T10,000. So for each of these cases, we see that the first first relative frequency corresponds to head, and the second element corresponds to the relative frequency of tails. So here again we see for T10, if you see this section, for when the total size was 10, probability relative frequency of head was 0.4, of that of tail was 0.6. Then when it became 50, it was close to 0.54, 0.46. Then again it went to 100, 0.53, 0.47. 1000, 0.49, 0.51. 10,000, 0.50, 0.498. So as we increase, if we make it a little more, if we increase it to 1 lakh, let's say I'll increase another 0. Okay. So again this is also tending towards 0.5. So as we keep on increasing the size, the number of times the coin toss experiment is repeated, the relative frequency of the event that we had defined earlier, that is getting a tail, that moves closer and closer to 0.5. Okay. So this was a demonstration of how we can approximate probability using the relative frequency by using the axiomatic definition of probability. Now, as I had also mentioned in the previous class, if you really want to gather the documentation of any function of your choice, either you could go and search over here, or you could find the help button. Yeah, you could go and click on the help button over here and get the respective function and get the documentation for that. Or you could also type question mark and then the sample function name. Let's say I'm interested in sample, so I'll write question mark sample and this thing will come up here. Okay. This information inside the curly braces will tell you which package is this function a part of. Alright, for example, if I want to see a documentation on table, I'll just have to write table, question mark table. So it will give me which package which package it is a part of, what are the kind of arguments that it is using, and some examples to supplement understanding. Alright, so and another way to do that is just to hover or take your cursor to that function and press F1. Okay, that will also open the R documentation for the respective functions. So is there any doubt from whatever I've explained so far? Any questions, any suggestions, anything? Alright, if not, then I'll just move on to the question answers. Okay, so back to this window. Can you please confirm if you can see my screen? Is it visible?
Yes, ma'am.
Okay. Alright, so I'll just move on to the question answers. Okay. So the first question is, in a medical experiment, 8 medicines numbered as 1, 2, 3, 4, 5, 6, 7, 8 have to be given to 8 patients. Then the sample space of the experiment is what? Okay. So 8 medicines, 1, 2, 3, 4, have to be given to 8 patients. Then what could be the sample space of the experiment? Now, medicine 1 could be given to any of the 8 patients. Medicine 2 could also be given to any of the 8 patients. So all possible outcomes of this set will be the sample space of the experiment. Okay. So if I have, let's say, patient 1 to patient 8, 1 could be given to 1, 8 could be given to 8. Or since it is a random experiment, medicine 3 could be given to patient 1 and 7 could be given to patient 8. So any permutation of 1, 2, 3, 4, 5, 6, 7, 8 could be given in any order to the 8 patients that we have. Okay, so this is just one such combination. Therefore, the sample space would be any permutation that is possible. So the correct answer is all orderings of 1, 2, 3, 4, 5, 6, 7, 8. Is it okay? Any doubt? Alright. So then I'll move on to the next one. Alright. The question is, suppose we throw 2 dice simultaneously and an event is defined as number of dots observed on the upper surface of both the dice. Okay. Suppose an event is defined as number of dots on first die, number of dots on second die. Then what will be the sample space of the experiment? So from the first die, we could have 1, 2, 3, 4, 5, 6. Anything could come up. And from the second die also 1, 2, 3, 4, 5, 6 could come up. So the total sample space will be any combination of these two. So it will be it could be 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Again, it could be 2, 1, 2, 2 and so on to 2, 6. We should note here that 1, 6 and 6, 1 are different events. They are not the same element of the set. This implies that 1 has come up from the first die and 6 has come up from the second one. But this implies that the 6 has appeared on the first die and 1 has appeared on the second die. So in all we would have 36 total elements in the sample space of the experiment, with combinations like this: 1 1 1 2, 2 6, then till 6 1, 6 2 up to 6 6. So the correct answer is option D. We just need to ensure that there are 6 into 6 elements in this set. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 25 26 27 28 29 30 31 32 33 34 35 36. Yes, we have. So here's a typo, sorry. All right, any doubt? Okay. Let's move on to question 3. Okay, so the question is that a coin is tossed until a tail appears. Suppose the outcome of head is indicated by H. Then sample space of this experiment is what? So sample space is set of all possible outcomes. So let's say if we throw a coin and tail appears at the first instance, so then the sample space would be, then the outcome would be T, tail at first toss. Okay. All right. So let's say the second outcome that is possible is tail at second toss. Head first, tail second. So then the element would be head, tail. Okay. Let's say tail appears at third toss. First tail appears at third toss. Then the element would be HHT. And so on and so forth. It could be HHHT, HHHHT, and on and on. Okay. So then the sample space of the experiment would be option C. Sorry, not option C, option D. Sorry, there's a problem in this thing. It should be tail.
Both C and D, madam.
Yes, here it is a problem in the options. 1 second. This
C
would
possible,
be
D also
T.
possible, madam.
No, this one. No, see, previous options were incorrect. I'll tell you why. Because here, if in the second element you see tail appears at the first trial, then we are not tossing a coin again. We are tossing until a tail appears. Okay. So here there was a mistake in me writing. This should be tail, and this should be head. So the correct option is then C. And any doubt? Did you understand? why I said that it was a mistake. So the correct sample size would be, or sample space, sorry, my bad, would be tail, head, tail, head, tail, head, tail, and so on, because the experiment stops when a tail appears. Is it clear?
Yes, ma'am.
Okay. Any doubt or questions? Okay. So if not, I'll just move to the next one. Okay. So the question is, the complement of the sample space for the length of the useful life of a certain electronic component is the set of points such that these four options. Now, the variable under consideration is length of life of a certain electronic component. Okay, so let T denote that time, or let's say, yes, time length where the electronic component is functional, or let's say in other words, lifetime of the electronic component. So if I have to define lifetime, then T should be always greater than or equal to 0. Okay, so lifetime is, let's say, in seconds or minutes. If I have to find out the set lifetime, then it should be composed of elements like T such that T is greater than equal to 0. Now the question demands that what would be the complement of this set. So complement of this set would be T such that T is less than 0. So if we look at the number line, let's say this is 0, the lifetime that is denoted by T should fall on the right side of this 0 point, right? If it is short lived, then T would be small. If it has a longer life, then T would be large. Whatever it is, the lifetime should be, you cannot say that lifetime of a certain thing is negative. That is not possible. Okay, so the lifetime set would always be, it is possible that it starts functioning and then and there it stops. In that case, the lifetime would be 0. Sometimes it might happen, no, you might bring a bulb or something, you plug it in, the moment you switch it on, it is gone, it is fused. So those are 0 lifetime events. Okay, but usually it will go on for, let's say, 2 days, 3 days, 4 days, 10 days, 2 months, 3 months, and then it will fuse or it will become non-functional. So lifetime is always greater than or equal to 0. Now the complement of that set, complement is this thing, this part is covered, so then the complement would be T less than 0. Is it okay? Can I proceed?
Yes, ma'am.
All right, thank you. So this question says that in a medical experiment, 8 medicines numbered 1, 2, 3, 4, 5, 6, 7, 8 have to be given to 8 patients. Then the sample space of the event that only the even numbered medicines will be effective is how much? Okay, so the event is that only even number of medicines will be effective. So then the correct answer is this. Event E is 2468. Alright. Next one. The sample space of, it's the same question. The sample space of complementary event that only the even numbered medicines will be effective. They are asking for the complementary event. So complementary event to this even numbered medicines is actually the odd number of medicines. So E is 1357. Alright. Okay. So suppose we throw 2 dice simultaneously and an event is defined as number of dots observed on the upper surface, and an event is defined as number of dots on first die, number of dots on second die. Then space of all such points for which sum is an even number. Alright, so all possible outcomes omega would be 1 1 to 1 6, then again 2 1 to 2 6, and so on and so forth. 3 1 to 3 6, and finally 6 1 to 6 6. So omega will be, the length of omega, n of omega will be 36. Alright. Now the event is that sum of these two numbers should be even. So then we'll see what is happening. So here 1 1 adds up to 1. 1 2 is adding up to 3. So this cannot belong to that event, this set. So this is not possible. Alright. Here only those elements are represented. Even what I mean to say is that even though the sum adds up to an even number, this is not the only combination which has a sum which is even. Since the question is that we want the space of all points for which the sum is an even number, this is a subset of the event that we are considering. Okay, one special case. But we could also have 1 5, let's say, where two numbers add up to being an even number. We could also have 2 4. Okay. So the correct answer is this one, option D. Here you see that all the combinations add up to being an even number. Now we have to be very careful to see, if we have to carefully observe and inspect that all elements are represented here. Let's say if 3 3 is not there, then also this is not a correct answer. Alright, and option B is incorrect because it has only single element. The elements do not conform to the sample size. Okay, E has to be a subset of the sample size. Here this set has only one, single element set. This set is it consists of single elements, but the sample size that we have, it consists of the elements of this omega. What I mean to say is that each of the element of omega is denoted by small omega. Small omega should be a number of the format a comma b, where a denotes the number that has come up in the first die and b denotes the number that has come up on the second die. Okay, if this format is not maintained, then this cannot belong to, then this omega has to belong to the sample space. Then only we can define events and subsequent things. Okay, but this format is not matching with these. Okay, it doesn't conform to the format of the sample size in question. So the correct answer is option D. So here we'll have in total how many elements? 18 elements. So we'll just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Oh, one is missing. 1, 1, 1, 3, 1, 5, 2, 2, 2, 4, 2, 6, 3, 1, 3, 3, 3, 5, 4, 2, 4, 4, 4, 6, 5, 1, 5, 3, 5, 5.
Ma'am,
Yes.
the ordered pair 5 5 is missing in option D, I guess.
In option D, yes. That's what I saw. Option 5 5 was missing. 6 2 6 4 6 6. All right. Okay. All right, I'll move on to the next one. Let's say this one. The measurements of the thickness of a copper conductor might be modeled with the sample size as the set of positive real numbers. So let E1 be an event which shows x lies between 10 and 12. 10 is included. And E2 is an event that x is greater than 11 but it is less than 15. Okay, the entire sample space is the set of positive real numbers. So R is my omega. Okay, the real line. Let's say this is the real line. Alright, E1 is defined as x less than equal to 10, less than 12. So E1 is this one, this part of the line. Alright, here wherever I'm putting first bracket, it means very close to 12 but it is not touching 12. Alright, so this set is E1. Any real number that falls within these 2 points will be considered as in the set E1. Alright, E2, what do we have? E2 we have 11 less than x less than 15. Then let's say this is 11, 12, 13, 15. So this way coming very close to 11 but it's not touching 11. So this area is E2. So there is a small overlap between E1 and E2. Then the question is, what will be the value of E1 union E2? So E1 union E2 will be either E1 or E2 or both. So E1 union E2 means either E1 or E2 or both. But this will be counted only once. Alright, so E1 union E2 would be starting from 10 to 15. This entire area, any element that falls within this range will belong to either E1 or E2 or will fall in this overlapping region. Okay, so the correct answer is E1 union E2 is option A, x such that 10 less than equal to x less than 15. Is it okay? Alright. Okay. So we'll move on to the next one. Here we see the measurements of the thickness of a copper conductor. Same question. Let E2 be x less 11 less than x less than 15. Then the complement event of E2 complement is how much? So same thing, I'm going to draw. This is the real line that we are talking about. Okay, and if this is 11, this is 15, this is E2. Then the complement of E2 would be how much? Complement would be this part, whatever is not in E2. Complement means not in E2. Okay, or it could be in this part. So the correct answer is either okay, so thickness of copper conductor, yes, so here we should have less than equal to 11. Okay, the correct answer is option D. Either it should be less than equal to 11 or it should be greater than equal to 15. Okay, and why it should be greater than equal to 0? Because the x in question is thickness and thickness can't be negative. Alright, so if this is 0 point, then this area and this area above 15, both 11 and 15 included, will be the complement of E2, because E2 doesn't include 11 or either of 11 or 15. Alright, can I move on to the next one? Okay. Alright, here again we have the same question, but we have been asked to find out what is E1 intersection E2. So this is E1, 10 and 12, and this is E2, 11, 15. So then this is intersection or and. It has to lie both in A1 and A2. So this will be this region of overlap. Alright, then E1 intersection E2 would be x such that 11 less than x less than 12, and that is option B. Alright, okay. Again the same question, E1 or E2 is 11 less than x less than 15. Oh, okay, this question is repeated. 10 less than equal to x less than 12. Let's say E1 is 10 less than equal to x less than, how much was it, E1? 12. Then the complement of E1 would be how much? Same thing. Here this is E1, 10 to 12. So E1 complement would be this 0 to this much and this onwards. So the correct answer is option C. Is it okay? All right. So here we have the same situation. E1 is this area 10 to 12 and E2 is this area 11 to 15. This is E2 and this is E1. So now we have to find out E1 complement intersection E2, which means present in E2 but not in E1. So this we can also write it as E2 minus E1. Okay, so present in E2 means that it will fall here but not present in E1. E1 is still here. So something which is present in E2 but not in E1 is this area, this to this. So the correct answer is x such that 10 less than equal to x less than 15. Okay, option number A. Is it okay? All right. Let us move on to this question. Here it says that a random experiment can result in one of the outcomes A, B, C, D with probabilities these respectively. Okay. Let A denote the event BC, B denote the event ABD, and then C the event C. Then what is the probability of A, what are the probabilities of A, B and C? So, probability of A would be probability of constituent elements B plus probability of C. A is composed of these two elements and these are obviously disjoint outcomes. So, probability of B will then be 0.1 and probability of C is 0.4. Then the answer is 0.5. Okay. Probability of B will be probability of A plus probability of B plus probability of D. That is 0.2 plus 0.1 plus 0.3. That is 0.6. And probability C will be probability of C itself, which is 0.4. Okay. Now note here, probability of event, this is exceeding 1, but it is completely fine. Okay, because these are different subsets defined on omega. Their individual probabilities might go up 1, but probability summation of probability omega, where omega belongs to sample space, this should always be equal to 1, and that is ensured here. 0.2 plus 0.1 plus 0.4 plus 0.3, 0.7 and here 0.3. Is it okay? Alright, so let us move on to the next one. Okay, it's the same question. No. So here they are asking, the question remains the same. Here they have defined complements, A complement, B complement and C complement, and they have asked for the respective probabilities. Now probability of A complement should be 1 minus of probability of A. Okay. Therefore, probability of A complement would be 1 minus probability of A. 1 minus 0.5 is 0.5. Probability of B complement should be 1 minus probability of B. Probability of B we took out the last time, it was 0.6. So this should be 1 minus 0.6, that is 0.4. Okay. And probability of C complement would be 1 minus probability of C, that is 1 minus 0.4, that is 0.6. So the correct answer is option 2. Alright. Okay. Here, a random experiment can result in one of the two outcomes, in one of the outcomes A, B, C, D, one of the four outcomes, sorry, with these probabilities, then you have to find out the values of each of these events. Okay, so here we have A, B and C, three events. So let us first draw a Venn diagram. Probability A has B and C. Okay, B has A, B and D. Let's say if this is B, it has A and D. Okay, and C has only C. Alright, sorry. C has only alright, then A intersection B will have probability of only the overlapping element, that is B, which is equal to 0.1. Alright, probability A union B will be probability of A plus probability of B minus probability of A intersection B. Okay, so if you remember when I was describing the axiomatic definition of probability, at that point I had mentioned that A and B have, or AIs have to be disjoint, that is, there is no element which is common between AI and AJ. AI intersection AJ should be fine. Only in that case probability of union AI would be equal to summation of probability of AI. Okay, but here since we have overlap, we are actually double counting probability A intersection B, so we have to remove one occurrence. Alright, so here we have probability of A has how much, 0.2, plus probability of B was 0.1 minus probability of A intersection B was sorry, here I made a mistake. Probability of A we have calculated in the previous problem. Probability of A was how much, 0.5. So here we have 0.5 plus probability of B was how much, it was 0.6 to 0.6 minus probability of B intersection C. So probability of A intersection B is 0.1. So minus 0.1, which is equal to 1. Okay. So probability of A union B will be equal to 1. And B intersection C is only element C. So probability B intersection C is 0. Sorry. Probability B intersection C is nothing because B and C are totally disjoint set. So here B and C, this is set B, this set, okay, this set is set B, and this set is set C. Alright, no overlap between B and C. Therefore, B intersection C is 5, and therefore probability of B intersection C will be equal to 0. So the correct answer is option number 1. Alright. Okay. So just as a recap, I'll so far any problems, doubts, you can ask me. Alright. No questions so far? Alright. So then, before going on to recapitulation, let us solve one question. So the question is, let's say a survey is conducted with 100 people. Asking each of them okay, so this is the question. There's a survey where 100 persons are surveyed and they are asked how many meals they have each day. Okay, and let's say here they reply the number of meals each day. Alright, so 100 people they are surveyed and they report. So let's say that person 1 says I have 2, person 2 says I have 3, person 3 says I have 2, person 4 says I have 4, and so on and so forth. Okay, so then from here what we can do is that from this raw data we can make a frequency table. Alright, so if we have the raw data, from the raw data we can construct a frequency table of this sort. Okay, where we in one column we are listing the number of meals each day, let that be 1 2 3 4, and here we have the absolute frequency. Alright, which is the total number of times 1 has occurred. So let's say out of 100 people, 20 people or 8, let's say 35 people have responded that they have 1 meal a day. So 35. 30 people have said that they have 2 square meals a day. Alright, so 65. Let's say 15 people said that they have 4 meals a day. So that makes 80, and 20 people have said that they take 3 meals a day. So this table is actually giving me the absolute frequency. Alright. Now if I want to have the relative frequency, then I have to divide 35 by total, that is 100. Okay, this is 30 by 100, 20 by 100, and this is 15 by 100. Okay, so if we get the question that what is the relative frequency of people that eat 3 meals a day, then the answer is 20% or 0.2. Is it okay? So relative frequency column would be the absolute frequency divided by sum of absolute frequency. So in order to get this absolute frequency, we have to use the table column in R, and then table by length would give us the relative frequency. Now let's say we have these frequency and we want to visualize this. Okay, so how can we do that? So here let's say I have 35 ones. Alright, so let us say replicate 1 35 times. Okay, so here we have, let's say, some subsample. Then we have 30. How many times? Okay, are you able to see the R screen? Okay, so 2 meals we had 30 times. Alright, so here I'll replicate 2 30 times. Okay, S3 would be, if I replicate 3 20 times. 3 20 times. Alright, and 4 15 times. So S4 would be replicate 4 15 times. Okay, so the combined sample will be C, S1, S2, S3, S4. Okay, table of combined sample is this. See, 135 times, 230 times, 320 times, 415 times. And table of combined sample by length of combined sample is giving me the relative frequencies. Now if I want to visualize, let's say I want a histogram. So in order to plot a histogram, I am going to use the command hist and then supply the combined sample. Main, I'll write histogram of meals per day. Okay, I can set the axis accordingly. Alright, so I can set the tick marks to 1, 2, 3, 4 as I required. So in order to do that, what I can write is XAXT equal to N, and then here I will write axis side equal to 1, comma at equal to sequence 1, 2, 4, or let's say I write 0 to 4. Or I'll write, let's say 0.5 to 3.5 at 1, something like this. Okay, I can't do that because at and label lengths differ. 1, 2, 4 at 1. Okay, so okay, now if I instead of histograms I want, if instead of absolute frequency I want the relative frequency, then all I have to do is I have to give density equals to true. Okay, so density equals to true will give me, sorry, the relative frequencies. Why is it not giving me? sorry, I have to give frequency equal to false. Yes. So if I give frequency is equal to false, then I am going to get the relative frequencies, and here I am going to get it as a density. All right. Okay. So this was how you can visualize these axis labels have to be set accordingly. All right, let's look into this documentation. Okay, so if I put here brakes equal to C124, or if I give C024, yes. So this is my customized histogram. So I have to specify what are the breakpoints on the axis that I want with this brakes command. The frequency equal to false command will output the relative density on the y-axis, and hist will give of the entire raw data would give me the histogram plot, and I can make changes. I can add title using main. I can also add y label using ylab. Let me add this relative frequencies ylab equal to relative frequency, and xlab would be number of meals per day. Okay, this is a histogram plot that we have obtained. Now we can use this export button to save it as an image. I can save it in either of these formats. I can also specify the heights, I mean the dimensions of the picture, and now choose the directory where I want to save this plot, put a name, and then save it. I could do this, or I could just save it as a PDF. As a PDF, or you could copy this to clipboard, copy plot, go to the desired application of your choice. Let's say you copy it so you go to export, copy to clipboard, copy plot, and then just paste it here after adjusting the dimensions. Alright, so this was all I had for today. So we learned about experiment, we learned about sample space, we learned about events, we learned about Venn diagrams, and we learned about simple and composite events, frequencies of events, both absolute and relative, and also we learned about the axiomatic definition of probability, and some properties like probability should always lie between 0 and 1, probability of omega is 1, probability of phi is 0. Those things we learned, and also we learned how we demonstrated how relative frequency can approximate probability when sample size n is large. And we also saw how to make a histogram in R, and some basic customization of the plot using breaks and freak arguments. Alright, so with this I'm going to end today's session, and before ending I would request all of you to speak up, and if you do have any doubts, this is the time you can ask me. All right. If there's nothing more, then thank you so much for joining. And if you do have doubts, you can post it in the discussions forum and we'll try to answer that. Okay. So thank you once again for joining, and I'll see you all next week. Thank you.